Thanks a lot. So I guess this is the last talk before the lunch. So I know that many people are hungry, but I'm going to try to make you as occupied as possible. So
but we want to go to the lunch with more angry.
You need to deserve that, right? So what we're gonna do is that I'm going to show you a damage formulation, and I know it's a pleasure to be here because I don't need to convince you that strain gradient elasticity is a useful model or tool, so you are all equipped with it, but I will give you some application in order to make a brainstorming that it may be used in that sense as well. And if you want to do a simulation, there are a lot of different numerical methods, but I'm going to use here something which I call a mixed finite element method. We will see what it is exactly. I'm coming from Uppsala University, which is 60 kilometers from Stockholm, from very north. We don't have that much of sun in Sweden, but it also gives us a pleasure to work a lot. So let me continue with first of all a kind of a maybe not a motivation, but more like an application. Where do we need the strain gradient formulation? So one stuff, maybe you also like these 3D printers or additive manufacturing, where you use your CAD, computer-aided design, your model, and send it to an STL file. So it doesn't matter if you use stereolithographic or something fused deposition modeling, or even like the metal-based system, you always use an STL file, which is then used in a slicer to generate layer by layer manufacturing. So there is, if it's a powder-based system, a laser moving, or if it's an extrusion-based system, a nozzle is moving, something is moving and putting material in different lines or different microstructure. So in the slicer there is an option, everybody likes that, which is the infill ratio. I don't know who started that, but it is somehow very much used in order to reduce the weight. So let me show you what it looks like. So I have here from the slicer a really technical application. It's boring, but I like that. I'm a mechanical engineer. And in this technical application, what you see here is these yellow parts. These are called walls. These are full material. And then inside there is this infill ratio, which is here 80%. So that means only 80% of the void is filled with material. What's the rest? So the rest is, this red part is with material, and maybe you can see some kind of void here as well. What is the rest is, you need to use a microstructure. And these slicer programs are pretty much using different grid type, lattice type, lines type, or even TPMS, triple periodic multiple surfaces. There are lots of different microstructures that slicer can use, and the user is normally using one of them without knowing what it is. So now here's the point. So we can use a little bit more exaggerated system, and I can show you even like what people use. I know you're engineers, you're getting like really loose on your seat, and then think like 10%, there's a lot of buckling and so, but just forget about it now. People are using that. People simply use 20-30% of infill ratio because they can reduce the weight. So now, if you have a look even in the 30 or 50%, I would never use 30%, but if you want to use that, but have a look in the microstructure. So the microstructure it's a repeating pattern, of course, and the characteristic length and the characteristic length of the whole geometry, they are in the same order of magnitude. So what it means is, we cannot still use the linear elasticity or Hooke's law that we normally use. So we need to invent something more generalized, and that's exactly the topic, as we all know. Strain gradient elasticity is something useful that we can use as an homogenization tool here. So I'm going to show you a generalized mechanics here, and I want to add also damage evolution. How can we make damage formulation and strain gradient formulation in a coherent manner? And then of course then we will have a bunch of parameters to determine and solve a system. So let us start deserving the lunch. First of all, what I use is, there are different methodologies, of course. What I use is using the principle of least action. So that means there's a Lagrange formulation. Why? We're gonna see in a minute why it is so useful to use that. There is a Lagrangian density, this is called L, and this depends on x. So x is coordinates, but not that only space coordinates, a little bit more of a mathematical term, it's space and time. So you can see it actually here in that small index, I'm using a Greek alphabet in order to give 1 to 4, which is like space and time. And then we have also phi, which is a variable, which we are interested in, like a displacement, for example. And then also the first derivative, because this is a first order formulation. That's what we do in classical mechanics. So if we want to extend, if we want to generalize this, then what we do is we add the second derivative. But this time the derivative is not only in space, it's in space and time. So that means we have here the interesting variable that we want to compute, which is displacement or damage. And then we have the first derivative and also the second derivative. So the interesting part comes if we really write what we are interested in. We want to have the displacement and we want to have a damage. This damage is omega. I'm using in a Kachanov sense, which is a continuous function between 0 and 1. So 0 means the material is intact and 1 means the material is fractured. So that means what we want to have is the displacement and damage and their first derivative, which we all know, and also their second derivative. But by using x as space and time, we have also the mixed derivative. So that means we have a first time derivative, here's the dot, but we also have the first space derivative. So second derivative may have one space and one time derivative as well. So we need to incorporate all of them, and it is easier if you use this Lagrangian kinetics. So if I now start doing it, I know it's a little bit manipulation, but I'm going to use a displacement, damage variable, and an additional variable. We will see why I need that. But this auxiliary variable, additional variable, is something in order to make the formulation correct, but I'm not going to compute it. So let me show what I mean. There's only one assumption, which is what is the Lagrangian. And for the Lagrangian, I'm using a model. This is a model. This may be right or wrong. So this is if in the end it's not good enough, I need to change that model. So what is this model saying? The first one is the kinetic energy that we all know, which is depending on the velocity, which is the rate of displacement. And that's it. So I'm making the life easy and saying the kinetic energy only depends on the first time derivative of displacement. Of course, now you can ask, yeah, where is the first time derivative and first space derivative, why they are not part of the kinetic energy? You're right, they're supposed to be a part of it, but I'm making as simple as possible. Then we have here an F, which is a free energy or the deformation energy in the system. So we need to talk about the deformation energy. There is this part which is G because of the gravitational load. So if the weight of the construction is important in making a deformation, then we have a so-called potential energy. So this first part is more or less, everybody knows that. Now we start with the damage formulation. In the damage formulation, I have the omega dot, which is the first time derivative of the damage variable, and this auxiliary variable. So this constellation is useful in order to have in the end a balance equation where we have the first time derivative. So that's the main idea of using this auxiliary variable. And then we have here something which is similar to the free energy here for the displacement. We have for the damage variable something, and the first derivative and the second derivative. So here the second derivative of the damage variable is coming automatically from the systematic view of saying I want to have the second derivative in the system. But way before that, people were using the second derivative of the damage variable in order to regularize the computation. And we will come to that, what it means. So we have two different stuff to choose, M and F, and I'm choosing them in such a manner that I will have in the end a formulation which is consistent with the literature. So first of all, we have the displacement field, and for the damage, I'm using a phase field variable in a simple manner between 0 and 1. So what we have is weak formulation, and that's all I need. Weak form for the displacement. So that means there is a test function of the displacement. If I solve this, out of that I can get the displacement field. What I need to have is, of course, the free energy here, and there is this so-called Cauchy stress or Piola stress, and here is the couple stress or double stress. And also for the boundary condition, I make my life easy and I just use traction, which is just the force per area. And then the second weak form is for the auxiliary variable, which I use for the damage variable, where you see the test function as for the auxiliary variable. And here, because of using that trick in the Lagrangian function, I can have the first time derivative. In the other one, I have the second time derivative. So that's the whole idea of using this trick, which I found in the fluid dynamics problems, that we can have a Lagrangian function which is bringing in something new and not using it and not solving it, because it's only necessary to get the correct evolution of the damage variable. So the rest is a choice. I make a choice in such a way that the formulation in the end is consistent with the literature. So first of all, I have the free energy, which is depending on the degradation function G. So this degradation function, I'm just going to use something, but it's important to choose. And then we have the standard deformation energy, which is depending on the strain gradient, and a mixed one, which is strain and strain gradient. So as you immediately see, we have this rank 4 tensor, rank 5 tensor, and rank 6 tensor. How do I know what they are? We need to determine these parameters. And then I'm choosing for the M something which is actually going back to Christian Mie, where he was using this, this function, which is just the maximum of the deformation energy. Because of using this trick, I can also have an irreversible damage formulation, so that if once the damage is increased, it can never heal. So there's no healing of the damage in the system by using this numerical trick. And then the rest I'm using like with an M, which is often called the mobility function or mobility parameter, which is controlling, so to say, the let's call it the inertia of the damage. And then we have also here a GC, which is directly related to the critical energy release rate. So now the second derivative, which is a bit of a challenge, I'm combining it with this first derivative in order to make the number of parameters one less. What I have here is an L. L is the characteristic length of the thickness of the fracture. So 2 times L is the thickness of the fracture, which has a direct change to the mesh, and I will get rid of the mesh dependency by using this one in the Lagrangian system. So how do we implement something like that? In order to be able to solve the question, solve the equations, I need to know that it has to be C1 continuous, because we have not only the first derivative but also the second derivative of displacement. In order to be able to assure the C1 continuity, I'm using a mixed finite element formulation. What it means is, in each node, I'm calculating the displacement, 2-dimensional, a standard Hilbert-Sobolev space, and also the displacement gradient is calculated as an unknown. So the displacement and gradient of displacement are unknowns, but of course I have to make it sure that the displacement gradient and this new unknown function are also the same by adding a Lagrange multiplier. So I need to also calculate the Lagrange multiplier, which makes it really costly. So what I do is I just use the trick which is known as Houellebecq principle. I'm just looking at the units and trying to find for this Lagrange multiplier something which is from the order of magnitude correct. Okay, so that means what I use here is a trick in order to skip or circumvent calculation of Lagrange multipliers. I'm replacing them with something which is okay from the unit, and the same trick I can use also for the damage. So I'm not calculating the Lagrange multipliers, but enforcing this additional constraint by using a Lagrange multiplier. So you can maybe find a commercial program and then try to implement all of that, but it's tough. So therefore I'm not using any commercial program. I'm using here open source packages to implement them. What I use specifically is a Salome, which is an excellent software where you can do the CAD design and do all the geometric boundary conditions and so on, which then uses, for example, NetGen as a mesh generator. And after that, I can import it in Phoenix by using Python module. It's a Phoenix project, which has started in Scandinavian countries, but is now all over the world. So the good part of Phoenix project is that the user has to write everything in Python. Python is good. We don't write any the constructor or garbage collector. It's easy to program in Python, but the program has a wrapper. So this Python code is being wrapped to C++, compiled and solved. So the solution itself is pretty fast, although we use Python in order to generate the input. And there are also some more nice features that I'm using. For example, symbolic derivative, which is good for linearization. It's not depending on the mesh. And then everything, all the assembly and so on, done in a really quick fashion. And after that, parallelization is no problem at all. I always use parallel computing. And also I have here used some other packages which are compatible with Phoenix in order to do remeshing, in order to do updated Lagrangian, so the mesh is moving and so on. All of these stuff are implemented, and it's pretty easy to implement. So in the end, we show everything in Paraview. So if you think like, wow, that's really nice to see, but I don't know where to start, then I can make an advertisement here. So there is a book which you can get, and then if you cannot get, you just write me an email, I will send you the book, and I'm allowed to do that. So, and this book has the really standard stuff like elasticity and plasticity, and also the code. So it's not only the textbook information about elasticity, but you also see the code. Not only the textbook information of plasticity, but you also have the code in it. And there is also a little bit more. So if you are interested in the coupling of thermomechanics and electromagnetism, you can find all the theory first and the code afterwards. So then you can immediately see how easy it is. Just write a 100 lines of Python code in Phoenix and get the job done. Because once you did it and you want to change the material model, it's just one line. And if you want to use the commercial software, then it's maybe really tedious task. So let's go back after the advertisement to the idea. What we want to have is this damage formulation, and we have seen this rank 4, 5, 6 are unknown. So I need to find a possibility to homogenize microstructure in order to get the parameters for rank 4, 5, 6. I'm using here an example. I'm using here an example where we have a geometry which is called a grid substructure. If you remember the inferior ratio, so this is actually inferior ratio of, I guess, 60%. So that means 60% of orange material is filling the space and the rest is void. So here is a void. I'm using this in order to construct the CGD. These are the rank 4, 5, 6 tensors. In order to be able to write them, I'm using something like a Voigt notation in 2 dimensions. This is the rank 4, rank 5, and rank 6 tensors. I need to have all these numbers, and how to do this is called an homogenization. So there are different homogenization methods. If I am not mentioning yours one, then please let me know. One of them is granular micromechanical modeling. So of course, Anil Mishra and Luca Palaci, they are the frontiers here doing that. This is perfect, but only works if you have a granular medium, so which we don't have it here. Another one is a computational homogenization, which is pretty solid, but the problem is you need to define all the different possibilities of stretching and shearing, and you have also some problems with the boundary conditions. So this is also not what I'm using. Another one is an asymptotic homogenization method, which is my favorite one, which I'm going to use it here in order to get all these parameters, which is better for the boundary conditions. And then the third one, fourth one is what I know is an SLB solution method, which is also really good, but then you have to have an inclusion which is round or spherical or star shaped, so you can find a solution for that, so it's not suitable here. So if I use the asymptotic homogenization on that particular material, with the orange material properties are given as linear elastic, then I get all these numbers. There is no assumption here. I'm not saying this has to be 0 and putting a 0 there. It comes out of the calculation that it is a really small number, so I can round and put 0. So I'm rounding here everything up to 1 digit. So, and luckily, so the rank 5 is all 0. That means, which we are expecting, the representative volume element is centrosymmetric. So that means if you have a point here and then go to a xy position and go to a minus x minus y position, you have the same void or material. In this constellation, this has to be 0, and it comes out also 0. without using too much of is this okay or not. So of course you can be skeptical. You can ask the question, are these numbers correct? I don't know. This is what the asymptotic homogenization comes out. But I can at least test one simple scenario in order to show that at least in this scenario they work. So what is the scenario? I'm making two computations here. One computation is really a detailed finite element mesh. This is a little bit transparent here, you can see. The transparent one is the material and void. They are all captured here. And another computation is the strain gradient homogenization by using rank 4, 5, 6, and everything is one material. So they are on top of each other. So you see the difference is quite small, and more importantly, by using mixed finite element formulation, I can guarantee a monotonous convergence. So that's what we see here, that the error between the detailed numerical simulation and the homogenized one is monotonously getting smaller. So at least for one scenario I can show that it works. So I'm assuming that for all scenarios it's working from the asymptotic homogenization method. And then I use it for another problem. Another problem I'm somehow like using an asymmetric notch. Why? Because if you use a symmetric notch, it's mode 1, mode 2, it's a bit boring. So I'm using an asymmetric notch here in order to have a mixed mode formulation or mixed mode fracture here in the system. And of course I need to make some assumptions like the mobility parameter and so on. But the most important part is the length scale. So this length scale is determining the thickness of the fracture. And I am merging it with the finite element length. So this mesh is automatically generated, finding out the smallest element length, and then saying 4 times is the L. So that means I'm giving enough many elements to go from 0 to 1, 1 to 0. So that's important to have a continuous and still okay fracture change. But of course, if you have a look, I'm using a quite coarse mesh. So that means the fracture will be really thick, and in reality it's not the case. In reality we should have a fracture thickness of atomic scale. So what is the problem here is by choosing a really coarse mesh I will have a really thick fracture. But luckily in the system I'm using the second gradient of the damage variable, which is an additional regularization to the system. So let me show what I mean. If I start pulling it, it's a transient simulation, then of course at the notch tip there is an initiation of the crack, which we expect. And then if I continue pulling, then we see this fracture which is really thick. So the thickness of that is because of the coarse mesh. And normally what people do is using a finer and finer and finer mesh. So normally if you use a finer mesh, then the thickness of the fracture will be thinner. But here, because we are using the second gradient of the damage variable, we don't need that. If you have a look in the displacement field, which is here, then you see a really sharp change of the displacement, and that jump in the displacement is exactly what we want to capture. So the second gradient of damage, which was also originally introduced, is an additional regularization to the system where we can still use coarse mesh, which is okay, the fracture is not looking perfect, but the displacement jump is what we want to capture is good enough. And this is now incoherent with the strain gradient formulation if we start from the Lagrangian formulation. So what we see here is an asymptotic homogenization method that I use for at least 3D printing kind of a problem. And the consistent generalization, because now we have not the second gradient of displacement or second gradient of damage, in a coherent manner coming automatically from the assumption, from the formulation, in order to be able to solve it, because now the system is computationally heavy. We have the displacement, gradient displacement, damage, gradient displacement, everything there. I'm using a staggered scheme, because if I use a staggered scheme, then I can use also some sort of like the solver bound that is between 0 and 1, it's more quicker. And all of these computations can be done in finite element method by using open source implementations. So what is missing is, of course, there is a lot of numerical problems. So in order to counteract that, we are now using also Hermite and Argy's finite element method, also IGA, but no, I'm not a big fan of it. And also what we are doing right now is these inertial terms. With my colleagues Jan Ionesco, we are asking the question, it is possible to find out this additional inertial terms in the formulation and how we can determine them. And of course, more multiphysics is what I like as a hobby, more like electromagnetism and thermomechanics are undergoing. With all do that, I would say let me make another advertisement. If you're interested to send to the special issue continuum mechanics and thermodynamics, just have a look in the square code. You will find in symmetry a special issue. I'm gonna treat you fair and quick. Send me your papers, and all of my papers you can find on the website and download them. With all that, thanks a lot for your attention.